Hello and welcome back to Aerospace and Mechanical Lab 2. Today we are going to talk about the last and final lab for the Aerospace and Mechanical Lab 2 series. We are going to discuss introduce computational fluid dynamics. Essentially, this is going to be in continuation of what we did for the last lab. It was computational mechanics. So we are going to do a recap of what we have learned in lab 5, a structural analysis. We are going to talk about numerical modeling again. We are going to move from finite element analysis, which is the method we use for the structural analysis lab, to computational fluid dynamics. Essentially same idea, different physics. We are going to discuss what is CFD. We are going to talk about the governing equations in a CFD case. We're going to talk about differences in meshing for fluids and solids. We are going to talk about the boundary conditions in computational fluid dynamics, convergence and residuals, and we are going to talk about the ANSYS Fluent workflow. We are going to discuss the lab 5 itself and what to look for results and what to include in your lab reports. Okay, so from lab 5 we have already learned about the workbench environment in ANSYS, which is essentially the workbench we are going to use to create our modules, our analysis, our simulations. We did learn about creating a geometry and design modeler, which is going to be the same software we are going to use for this lab as well. We did learn about mesh generation and applying boundary conditions and loads, and we did learn about solving and viewing results. So lab 5 was focused on solids. We did apply forces and then observe deformation and the stress, which essentially means that we did solve in the back end, we did solve the equations of solid mechanics, equilibrium equation and stress strain equations. For lab 6, which is focused on fluids, we are going to define flow. We are going to observe velocity and pressure distributions and pressure heat maps and contours. We are going to solve the Navier-Stokes equation, which essentially means that we are going to solve the conservation of mass and momentum equation. This is done by the solver, not by you. Okay. The idea of numerical modeling, numerical simulations, is that we have a lot of complicated scenarios that cannot be tested in a lab, or we don't really have an analytical solution so we cannot use a pen and paper. The numerical modeling is going to simplify the complicated models out there, and is going to let us essentially break these complicated scenarios into smaller pieces and then solve those pieces and get them together, essentially. The steps we need to follow always is we need to define a domain. We need to divide our domain into smaller pieces. We need to talk about the governing equations. We need to apply this correct governing equations for each piece, and then we need to solve the system of equations and then interpret the results. Okay. In lab 5, we did use finite element analysis to analyze the solids and structures. Our inputs were forces and supports. The output was stress and deformation. The equations we used was the equilibrium structural equations and the Hooke's law, and our tool was ANSYS Mechanical. In this lab 6, this should say lab 6. In this lab, we are going to analyze the fluid flow. Our inputs are velocity and pressure boundary conditions. The outputs are velocity and pressure fields over the domain. And the equations we use are the Navier-Stokes and the continuity equations, conservation of momentum and mass, basically. And the tool we are going to use is ANSYS Fluent. Okay, so where do we use computational fluid dynamics, or in short, CFD? Essentially, we use it everywhere where a fluid is moving. This fluid can be air, can be water, can be anything. It can be a very complicated flow or a very simplified flow. And it has a lot of applications. CFD in aerospace, automotive industries, civil engineering, biomedical, and the energy industries. The governing equations, very simplified version of the governing equations that are used in the back end of the softwares to analyze the flow, are these three: conservation of mass, which essentially says mass in is equal to mass out. conservation of momentum, which is essentially the interpretation of Newton's second law in fluid mechanics, in fluid flow, and conservation of energy, which is the interpretation of first law of thermodynamics in fluid flow. Again, for our scenario, we don't really care about conservation of energy because there is no heating or cooling involved. It's just a fluid flow. So we are going to only use these two sets of equations to solve our problems. Okay, so meshing is essentially similar to what we did in the previous lectures. We are going to do in the previous lab, we are going to divide our domain into smaller cells and then solve the governing equation for each cell and then relate the cells together. Of course, the finer the mesh, near where you have most of the changes, which is usually near the walls and the obstacles, the better. And the coarser the mesh where there is no action, that also saves a lot of computational time. We want to make sure that our mesh is good quality mesh. The skewness should be below 0.9. We're going to learn how to actually check the skewness of the mesh. And the aspect ratio should be small of the mesh. The general idea is if you have more cells, your results are going to be more accurate, but the solver is going to be slower. Okay, what is it that we are going to set for our boundary conditions? Our geometry is essentially going to be a small square in a bigger enclosure or control volume, right? And for this, we need to define an inlet where the fluid comes into the control volume, where we need to define an outlet where the fluid goes out of the control volume. And we are going to define walls, which are essentially solid boundaries of that square. And we are going to use no slip condition for the wall boundaries. And that no slip condition means that there is fluid velocity is 0 at the wall surface. And the obstacle we have essentially is a wall, of course. And then we need to run the simulations until our simulation has converged. You want to keep in mind that CFD solvers do work iteratively. What does it mean? It means that they start with an initial guess and then solve the problem based on that initial guess and then compare the final solution to that initial guess, right? As soon as that difference between the initial guess and final solution for an iteration becomes smaller than a set value, that means that we have reached a solution, or a solution is converged. So the general idea is your error, which is the difference between the final solution of each iteration and the initial guess of each iteration, becomes smaller than a set value, and you have reached a specific solution. That set value is what we call the residual. Residual essentially is what remains, the set residual. Residual itself is a measure of how well the governing equations are satisfied at each iteration. Meaning that residual is the difference between the initial guess and the final solution for each iteration. Of course, we want it to decrease over time. Our set value for residual is usually around 10 to the negative 4. And then we might get to instabilities or oscillations in residual. We don't really, that is not a good scenario. We will never reach convergence if that happens. So we need to go back and change your mesh or initial conditions or inlets or whatever. And we want to start with 500 iterations. Again, this is going to be discussed in more detail later on. And we want to watch the residual plot in Fluent. Again, all of these we are going to learn more about later on. And whenever your residual line becomes flat, it means that you have converged to a solution. Okay. The workflow is we start from the design modeler to create our geometry. We go to meshing, we go to Fluent, which is the different part of the workflow. Then we go to solve the Fluent problem, and then post-processing. that can be done inside the Fluent software or in the post-processing software that is given to us by ANSYS. And in ANSYS Workbench, all of these are connected, as we're going to see in a very, very short time. Okay, so what is it that we are analyzing? This is lab 6, I'm sorry. This is, we are going to analyze the flow around the square. This is a two-dimensional simulation. Our control volume, which is essentially the enclosure around the square, this is the thing that we didn't have in computational mechanics, is supposed to be 1 meters by 1 meters. The obstacle itself, the square itself, is 20 centimeters by 20 centimeters. We're going to use a Boolean operation to remove the square from the control volume, because that fluid domain is a domain of interest, not the square itself, unlike the previous lab. And we are going to test a laminar flow model. The material we are using here is air, and we have two different scenarios: one with inlet velocities of 0.01 meters per second, two with the inlet velocities of 0.1 meters per second. Okay, and in your lab report, we are going to need you to present velocity vectors, pressure contours, path line, and streamlines for the two different scenarios. Okay. Of course, this is the expectations for the two different velocities are going to be different. We mainly expect to see flow separation at high velocities and larger wake region at higher velocities. If you don't know what these are, we're going to talk about those in the lab recording. You can also go back to your fluid mechanics, do a review of, I think, chapter 6 of the fluid mechanics book to remember all of these things. And yeah, the main goal for you is to learn how to use ANSYS for CFD, to learn what CFD is, and then compare these two scenarios as far as the fluid mechanics go. In your report, you need to have a screenshot of your mesh, a path line for both velocities, pressure contours for both velocities, velocity vector for both velocities, and you need to have a discussion about what happens when you change the velocity, and you'll need to comment on the mesh quality. And you need to submit the ANSYS project file to Blackboard, but that is a requirement if you, for whatever reason, are missing the lab. So if you are in the lab and if your TA is there, is seeing you, you do not need to submit your project file to Blackboard. So that is a discussion between you and your TA. And that is it for today. Thank you for listening. Please let me know if you have any questions or concerns.